This is Advent of Cyber Day 17, and this challenge is called Filtering the Order Amidst Chaos. After handling unrestricted file uploads and SQL injection vulnerabilities, McSkitty continued to review Santa's web applications. She tumbled upon users-submitted inputs that are recognizable, and some are even bordering on malicious. She then discovered that Santa's team hadn't updated these web applications in a long time, as they clearly needed more controls to filter misuse. Can you help McSkitty research and learn a useful technique to handle that in the future? At this point, we are already well aware of the security concerns regarding input validation, analogous to being the castle wall of your application that forms the first line of defense against an array of scenarios from harmless misuse to outright malicious intents. Validating input merits the same effect as its medieval counterpart in terms of its hardening. It goes without question that insufficient effort in this space may result in attack vectors being vulnerable and consequently exploited in your application. Day 15 talked about input validation in light of unrestricted file upload, while Day 16 focused on SQL injection. In this task we'll be exploring input validation in a more general sense before touching upon one of its most complex use cases, free-form text fields, followed by a quick discussion on how you may move forward in your secure coding journey beyond input validation. Input validation foundations. Generally, an effective way to validate input is first to know how a specific piece of data is going to be processed by the rest of your application. The Day 15 task is a beautiful example that shows more or less the mindset required to be able to effectively tackle a specific case of unrestricted file upload. Data then goes through syntax and semantic validation checks to ensure that the user-provided values are both proper in their syntax, the answer follows the proper context asked by the question, and logical value. The values make sense for the question. In Day 15, you cannot manually type your CV in the input field. The form asks for a file, so it's simply not what's being asked. And you cannot just upload any file. It should follow a set of very specific rules, the implementation of which was all discussed in the latter parts of the task. Then comes whitelisting, where you can be very specific with what forms would accept and immediately strip or even drop the ones that don't fit in the predefined allowed category. HTML and regex. HTML's built-in features help a lot with the validation of user input, minimizing the need to rely on JavaScript for the same objective. The input element specifically has an array of very helpful capabilities centered around form validation. For instance, the input type, which can be set to specifically filter for an email, a URL, or even a file, among other things, promptly checks whether or not the user provided input fits the type of data that the form is asking for, and so feedback on its validity is immediately returned to the user as a result. For even more granular control of the input being provided, regex can be integrated into the mix, simply using it in the pattern attribute with the input element, and you're all set. Here is a nice resource to get started with regular expressions. A couple of examples shown below. So this is a regex pattern for lowercase, uppercase letters and numbers, and this is a pattern for emails that must have at tryhackme.com. Regex 101. This section will talk about some regex tips to get you started. To match any lowercase character from the English alphabet, the regex pattern is inside of square brackets, lowercase a dash lowercase z. We can deconstruct it as it follows. The square brackets indicates that you're trying to match one character within the set of characters inside of them. For example, if we're trying to match any vowel of the alphabet, we construct our regex as follows: A, E, I, O, U. The order of the characters doesn't matter and will all match the same. Square brackets can also accept a range of characters by adding a hyphen, as seen in our original example. You can also mix and match sets of characters with a bracket, so A-Z, then A-Z again. It means you want to match any character from the English alphabet regardless of case. While A.Z 0.9 means you want to match any lowercase alphabet character. We also need to talk about regex operators. The simplest one is a wildcard operator denoted by a dot. This means regex will match any character and is quite powerful when used with the operators asterisk or plus and min-max. The asterisk or star operator is used if you don't care if the preceding token matches anything or not. Or the plus operator is used if you want to make sure that it matches at least once. The curly braces operator, on the other hand, specifies the number of characters that you want to match. Let's look at the following examples. So this one here is saying that we need at least one or more alphanumeric characters. This one here is saying that the string must start with one or more letters, and then those letters must follow 0 or more numbers. So the caret symbol is used to denote the start of a string that regex is matching, and the dollar sign is used to denote the end of the string that's matching. So this one here is saying the string must start with a letter from A to Z, and it must have at least 3 to 9 character matches, and then the string ends. This one here is saying it must start with 3 letters, and then it can end with 3 of any character. There's also the concept of grouping and escaping, denoted by the parentheses for grouping and the backslash operator for escaping. Grouping is done to manage the matching of specific parts of the regex better, while escaping is used so we can match strings that contain regex operators. Finally, there's the question mark operator, which is used to denote that the preceding token is optional. Let's take a look at the following example. If we want to match both www.tryhackme.com and tryhackme.com, our pattern would be this. So the string can start with www. But the question mark says there can only be 0 or 1 of this, and then it must end with tryhackme.com. So this pattern would also avoid matching .tryhackme.com. It's also imperative to know that the wildcard operator can lead to laziness and consequently misuse. As such, it's always better to use character sets through the brackets, especially when we're validating input as we want it to be perfect. So a table to summarize everything. Square brackets is for character sets, matches any single character range of characters inside. Dot's a wildcard, asterisk is matching 0 or more, plus is matching 1 or more, min-max specifies how many characters it should match, parentheses is for grouping parts of regex, backslash is for escaping regex characters to be used as a character to match, question mark is for whether the preceding token is optional, the character still specifying the beginning of the string, and the dollar sign is for the end of the string. The unique case of freeform text. All of the techniques that we have covered in this task thus far are mainly concerned with structured data. Data that we already expect what it should look like. However, compared to the validation of structured data, free text is more complex and not very straightforward. Structured data have inherent characteristics that allow us to set them up quite quickly. For example, names shouldn't consist of special characters. Some names have, but these can be whitelisted. And age should only consist of numbers with an absolute maximum of 3 characters. Syntax and semantic validation checks can be immediately done on them, and the chaos suddenly doesn't seem too bad. In contrast, free text fields are more free-for-all, and so validations checks are more limited, and the challenge of securing it is generally vaguer. Yet, like all great engineers before us, we power through these challenges and make the best with what we're given. Listed below are some considerations to ponder on. First, we start again with the question of how this piece of data is going to be processed by the rest of the application. What will be the context for which this freeform text will be used? Free text fields for blog posts are tackled very differently than text fields used for a small comment section or a descriptive text field. Is the free text field necessary for your business purposes in the first place? Or could it be implemented differently, while still achieving the same goal? This is essential to know too, as part of writing secure code is avoiding writing vulnerable ones. Then we go to the tricky part. Since syntax and semantic checks are pretty much impossible due to the nature of free-form text fields, our best bet in having a bit of control is through whitelisting. There was cheap sheet lists down the general techniques to perform whitelisting, which can be summarized as follows. Ensure no invalid characters are present through proper encoding, and whitelist expected characters and character sets. Best remediation tactic. For the next part of the discussion, let's take a look at the simple base code below wherein a programmer attempts to retrieve the user details from a user. So you've got name, birthday, email, age, favorite website, and then a text area. The example is a bit bare and would have been an immediate nightmare as it raises many alarms not only in terms of security, but also in terms of risking getting a ton of garbage responses. Since all of them are text inputs by default, the birthday and age fields may receive responses that aren't within their specific context. Further, malicious users have free reign over the fields, essentially allowing them a free playground to tinker with. This is the case if no input validation is done at all. Let's fix it up a bit and review it again. So these fields now have types of text, date, email, number, URL. The changes above are literally just additions of the type attribute and their corresponding values within the input element. Yet there's already a world of difference between this one and the base implementation prior. Take note that security wasn't the main focus of these changes, yet it succeeds in mainly alleviating the chaos that the prior implementation otherwise invited. Going back to the discussion above, this is an example of the syntax check before done in the HTML layer. However, the implementation above is still susceptible to misuse, especially for naughty users. Let's fix it up further and review again. So the name has a minimum length of 4, max length of 70, required the date used for ages is from 1900 to 2014, and the email is now using a try-hack-me regex pattern. These semantic checks follow the proper business context to be effective. For example, the implementation above is geared towards the try-hack-me staff, marked by the email field only accepting track me emails. Furthermore, applying the foundations of input validation not only ensures that the data being provided is proper, but it also drastically limits the attack surface of the input fields, especially those requiring structured data. This is the reason why we haven't touched the text area field at the very end of the code block. As discussed earlier, free-form text is unique in such a way that applying syntax and semantic checks are pretty much impossible. In order to secure this one, we would first need to define what context, e.g. characters, character sets, symbols, etc., is acceptable, and then perform the actual whitelisting. Even then, it wouldn't be enough as it's still a very open field, and so techniques such as output escaping and using parameterized queries, among others, should be implemented as well. Client side versus server side. Our discussion until this point has been geared towards using input validation to ensure that the piece of data that we're getting from the users are not garbage. Proper input validation on the client side limits misuse and minimizes the attack surface of the application. However, it doesn't actively cover malicious use cases. As opposed to the above examples of validating input implemented on the client side, output escaping and using parameterized queries are implemented on the server side, adding computational load to the server, but ultimately helping in securing the application as a whole. This is done as an exercise of inherent distrust in the user-provided input despite validation. The example below uses the HTML entities PHP function to skip any character that can affect the application. On the other hand, the one below uses the HTML purifier library to help with some use cases, such as our text area conundrum above. Both examples are done on the server side to escape characters and purify content, respectively, both effective ways to prevent user misuse and cross-site scripting attacks. Implementing both client and server-side validation ensures that no stones are left unturned. This exact case highlights the importance of layering defenses and shows point-blank the limitation of client-side input validation. It also gives rise to the notion that input validation is not a one-stop shop for securing your application. Specific cases warrant specific security requirements, and so on this fact alone, it's already apparent that there exists multiple ways of attacking the challenge of securing user-provided input, and most of the time, they are implemented on top of each other. Input validation is an important layer of security that all production-level applications should have. However, no matter how perfect your input validation is for your specific use case, there simply are limitations to all kinds of security implementations, and input validation is not exempt from it. You cannot make your application fully cross-site scripting proof through input validation alone. Controls may be put in place at the input level that may lessen the attack surface of the application, but it doesn't fully remediate it. Full remediation of cross-site scripting vulnerability in your application requires additional layers of defenses, such as mitigation on the browser level, via secure cookies, content security policy headers, etc., and escaping and purifying user-provided input. In light of these remediation techniques, it makes sense to tackle each challenge on its own. SQL and LDAP-related vulnerabilities are addressed differently from cross-site scripting, so why try to fit them all in the same formula? Despite being an important security control, due diligence in security applications involving user-provided input should not stop invalidating the input per se. As seen in the previous examples, user input may be valid, but it doesn't necessarily mean that it's harmless. There are a lot of tools and frameworks out there that, when used properly, can help secure your application. For instance, HTML5's feature can help in minimizing input from misuse, while the use of regex can help filter out what we need from the user more granularly. We took a close look at regex here, especially because of its powerful capability to implement filters, and while the above examples aren't directly concerned about application security, they help minimize the attack surface of the application, which is further tackled through server-side validation techniques such as output escaping and using parameterized queries. We should be realistic and not try to solve all security problems with input validation. There is not one control that could prevent persistent malicious actors, and so layering these controls is the better way to move forward. We've prepared a regex exercise that you can access through the machine provided, so I'll start the machine and be right back. Okay, so the machine is started and I've gone to the regex practice directory in the terminal, so let's continue with the challenge. We are aware that some structured data are more complex than others, so we have set a specific syntax you may follow to make the exercise simple. Have fun. Filtering for usernames, alphanumeric, minimum of 6 characters, maximum of 12 characters, may consist of upper and lowercase letters. We can run it by doing Python 3 and regex header. So that pattern would be A to Z, A to Z, 0 to 9, and this would be 6, 12. Let's see. Okay, so that matched 1, 2, 3, 4, 5, 6, 7, 8. So we put 8 here. That was correct. Filtering for usernames. One username consists of a readable word concatenated with a number. What is it? Run that script again. So that would be AZ, AZ. This would be plus, because it has to be more than one. And then this is followed by 0 to 9, like so. I think because it's only matching 1, it has to be like that. Let's see what that produces. Yep, okay, user 1. Is that not correct? Maybe it's this one, user 35. Okay, that's interesting. Okay, let's continue. Filtering for emails, how many emails fit the syntax above? So we can run this again, and the syntax follows the form local-part at domain, without quotation marks. Local part is a random string, and the domain is in the form of domain name.tld. So I guess the pattern would be dot plus at dot plus slash dot com. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so let's 11. So filtering for emails, how many unique domains are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay, there we go. Filtering for emails, what is the domain of the email with the local part? lewisham44. That is amg.com. What is the domain of maximax? fedful.com. And hotmail.com, that's hussein.vault. Okay, now we need to search for URLs. URLs start with either HTTP or HTTPS. So it's HTTPS that :// Then inside here needs to be www slash dot question mark dot asterisk slash dot then az3. Okay, well that returned an error. Okay, mistake right there. So I'm going to copy this and we can retry. Okay, there we go. So there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 URLs. And there's 1, 2, 3, 4, 5, 6, 7 HTTPS URLs. So that's day 17 of Advent of Cyber completed. If you like this video, make sure to like and subscribe.